So, sometime earlier, we have discussed um, discussed about the behavior of ideal gas. But that time we were discussing it in the regime of classical mechanics. But now we will have a treatment within the quantum mechanical approach, and we will see that this ideal gas belongs to the ensemble system, canonical ensemble, or grand canonical ensemble. So this is what we are going to discuss today. Now, when we are telling about the thermodynamics of canonical ensemble systems, the most important thing which we have to talk about is the partition function of the system, right? So we have already derived that partition function for a canonical ensemble system. QNVT is equal to sum over E raised to minus beta E. We have derived already this expression. And in this one, we know that we always consider that there is a total energy, which is sum over Ne E. So what is Ne here? Ne is the number of particles in the energy level E. Like we are talking about a situation where we have different energy levels, like so we have 1, 2, 3, 4 being the names of the energy level 1, 2, 3, 4. So in the energy level 1 we will have N1, 2 we have N2, 3 we have N3, and 4 we have N4 number of particles. So that is what the Ne means by. N4 number of particles, right? In the fourth level, and so on and so forth. And therefore, and also then, which means that I can always write N1 E1 plus N2 E2 plus N3 E3 plus etc. So this is how we add the total energy. Equation 2, and then sum over Ne. This will give me total number of particles here. So these are the assumptions on which we start the discussion. And equation 1 can always be can always be extended, including the statistical weight factor, right? We have already written that also. So therefore QNVT can be written as sum over Ne G of Ne e raised to minus beta sum over Ne E. So this is another way I can write the equation number 1 by including the statistical weight factor. So this statistical weight factor over here corresponds to a distribution set Ne. So what is the distribution set means by? So I can have, so for example, I have say 6 number of particles. Okay, 6 particles. I can choose various configurations in which it can get distributed, right? I can always say I have 6 particles and 4 levels. There can be different kinds of distributions, right? So one of the distributions possible is that 4 0 2 0. So this is one of the distribution set possible. Another distribution set possible is 3 1 1 3 1 1. This is another distribution set possible, and so on, and like that. There can be the number of distributions possible, right? Like 4 1 1 0. This is another distribution set possible. So there can be different kinds sets of distribution sets possible. So that is the distribution set possible. So G of NE is a statistical weight factor corresponding to a particular distribution set NE. Okay. Okay. Now what we have to do is that in order to discuss this thing, now we know there are when we were deriving the partition function in such systems, and when we were discussing the behavior of the ideal gas, 3D ideal gas in the classical mechanical version, we were not really concerned about the kind of statistics it behaves. Now we know that there can be 3 kinds of statistics: Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein statistics. We already know that this kind of information are here. So in the rest of the discussion, we will be putting forth this new knowledge also in place. Okay. Now, in order to discuss further about the partition function, what do we need further? We need an idea of the G of NE. So what can be the value of G of MB with distribution set NE, right? So that's the first question. So we have to write similar expressions for FD and the B statistics. So G of MB NE, I can write it as product over E NE factorial. Why? So how do you explain that phenomenon? Some of you must have already got it. Why? That is why. Sorry, I did a mistake. 1 by NE factorial. Okay, sorry. Is it type? Okay, and then product over E 1 by NE factorial by mistake. So how do we get this 1 by NE factorial over here? Let me explain it this way. Now, for example, imagine that I have 4 levels, right? And like the example which we have written over here, there are 4 levels, 6 particles. As far as the MB statistics is concerned, the particles are considered to be distinguishable, right? So I have to mark that distinguishability in the level. So I am considering the first configuration over 4020. So the indistinguishability is inbuilt into the MB configuration. So all my particles has to be distinguishable. So these are the 4 particles I have arranged in the in the level 4, and the level 2, let me put another 2 particles. Yeah, so I have put 6 particles in, I have arranged 6 particles in 4 different levels now. So my question is that how many different ways of arranging these 4 particles in the level 4? It will be 4 factorial. How many of this one? This will be 2 factorial. That is n factorial ways of arranging this. So therefore, what are the total ways of arranging these 6 particles in this configuration? So that is how we will explain this one, right? Therefore, I can always write this probability. So what is the probability? Probability is inverse of the total number of possibilities, right? So the probability can be 1 by n factorial. So for the 4th level, I have 4 factorial, because there are 4 particles, and don't get confused with 4th level and okay, instead of 4th level, let me put this as level 1, level 2, level 3, level 4. So that will kill down that confusion. So the level 1 is having 4 particles. So therefore I have 4 factorial number of possibilities, or its probability of having one configuration like this arrangement is 1 by 4 factorial, right? For example, in the level 3 I have 2 particles, and there are 2 factorial ways in which I can arrange them, which means that for having this configuration, triangle and the sphere, it is 1 by 2 factorial. So what is the total number of possibilities? So then I can write G of MB is equal to 1 by 4 factorial into 1 by 0 factorial into 1 by 2 factorial into 1 by 0 factorial. So this is how I will write, right? This is exactly what I have written here. Product over E 1 by NE factorial, right? This will come to be what? 1 by 24 into 1 by 2, right? 1 by 48. So this is how, so G of MB over there can be evaluated like this. But my question is that now, so this is how the equation number 5 comes. So let me continue with the same example. So this is for the MB. And what will happen if in the case of FD, the Fermi-Dirac and the Bose-Einstein. Okay, let's take the Bose-Einstein itself in the beginning. So I have 4 levels and 6 particles. But in Bose-Einstein configuration, particles are considered to be indistinguishable, which means that I don't have the luxury of representing different particles in different manners. So therefore I can simply put everything in circles, right? Because none of these particles are distinguishable to each other. So they are indistinguishable. They are all identical particles. So therefore I can just simply put like this or there. So how many ways of arranging this kind of, so this is the level 1, this is level 2, this is level 3, level 4. So this level, there is only one way of arranging it. Whichever you arrange it, the 4 particles has to be in that level. So there is only 1 factorial possibilities over here, and there is only 1 factorial possibilities over here, right? So the total possibilities is 1 by 1 factorial into 1 by 0 factorial into 1 by 1 factorial into 1 by 0 factorial, which is 1, right? So G of BE NE is equal to 1. Similarly, what will be the case of FD? In FD also, the particles are indistinguishable. But, okay, let me put these are the levels. But here I have another limitation compared to Bose-Einstein. What? I can have only one particle in one level. Right, that's what the Pauli's exclusion principle talking about. In the last, one of the last videos, previous videos, we have proved that also. So I cannot have four particles in one level of FD, right? So I cannot be arranging this way. I can have only four particles maximum. I cannot have two particles in the same thing. My only variety is that I can have one particle in one level or no particle in a particular level. That's the only thing. So any can be 0 or 1. Whereas in the Bose-Einstein, any can be any number, 0, 1, 2, 3, 4, any number. Whereas in Maxwell-Boltzmann, it can be any number of particles, but all those particles are distinguishable. So here in the G of FD, like here, I can write it as is equal to 1 by 1 factorial into 1 by 1 factorial into 1 by 1 factorial into 1 by 1 factorial, which is again 1. Right? So G of FD is also equal to 1. G of Bose-Einstein is also equal to 1. Okay, so let me, so that is how, so the G of MB is equal to product over E 1 by NE factorial. So similar to that, we can write for as MB, for B as G of B for the distribution set NE is equal to 1 for all values of NE. So this is equation 6. G of FD is G of FD for the constant set NE is equal to 1 for NE equal to 0 or 1, right? Is equal to 0 for all other values of NE, right? So that is for one of the levels G of NE, for 0 for all other values of NE. So that is how we can talk about. So now what we have? Now we are in a position where we have found out the values for G of NE in three different statistics, namely Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac. Now we will substitute this number into here and see what is the partition function which we get. So that is how we will derive it for the Maxwell-Boltzmann statistics. So we will continue we will discuss that in the next video.